Hello, in this video we are going to attempt to solve the non-linear ordinary differential equations, first order ordinary differential equation dy by dx minus y tan x equals minus y cubed sec x, and we've called that equation 1. In order to solve this equation, we need to kind of simplify things a little bit and then use a substitution. So what we do is we divide throughout by minus y cubed, and hopefully the reason will become clear. So we divide by minus y cubed, and what we get is minus 1 over y cubed dy by dx minus y over y cubed. Actually, that becomes a plus because we're dividing by minus 1 over y cubed. We've also got the tan x components in there, and that is equal to sec x, and we'll call that equation 2. Right, okay. Now what we're going to do in the next stage is to use the substitution by letting, we'll just say let v equal 1 over y squared, and we can rewrite that as y to the minus 2, or y to the power minus 2. Now, if we differentiate both sides of that expression with respect to x, we get the following, which is dv by dx is equal to, well, the derivative of y to the power minus 2 is simply minus 2 times y to the power minus 3, and then you have to differentiate the y with respect to x, and that is equal to minus 2 over y cubed dy by dx. Right, so what we can see from this is that dy by dx is equal to minus y cubed over 2 dv by dx. So substituting, we'll call this equation 3. Substituting equation 3 back into equation 2 here, we obtain, and I'll just write this down, so we obtain minus 1 over y cubed multiplied by minus y cubed over 2 dv by dx. Then we've got a plus. Well, if you remember, if we just go back to equation 2, we had y over y cubed. That is the same as 1 over y squared. So we've got 1 over y squared times tan x, but we need to substitute in something for the 1 over y squared. Well, we know what that is, and it's equal to v. So we've got v tan x equal to sec x. And we can simplify this. And what we get is, well, as you can see, the y cubes there cancel out. The minus signs cancel out, giving us a positive value. So what we're left with, there we are, is a half dv by dx plus v tan x equals sec x. And we'll call that equation 4, just in case we need to refer to it again. Now, we'll simplify that a little bit further because we don't want the coefficient of a half in front of the derivative of v with respect to x. So if we multiply by 2, so multiply throughout by 2, we get dv by dx plus 2v tan x. In fact, we'll write the tan x first and put that in brackets. So we've got 2 tan x, and we'll put that in brackets times v, and that's equal to 2 sec x, and we'll call that equation 3. We'll call that equation 5. Okay. Now, for those of you who are familiar with linear ordinary differential equations, because what we've effectively done is to linearize this equation. We have no coefficients here in terms of v. We've only got coefficients in terms of x. So we now have a linear ordinary differential equation. Now I'm going to write that down on the next page because there isn't very much room there. So we've got dv by dx plus 2 tan x times v equals 2 sec x. And as on the above line, we called that equation 5, didn't we? Right, so I'm just rewriting it there again. Now, for those of you who are familiar with solving linear ordinary differential equations, which is what I've said this equation is now, we have to find an integrating factor. So the integrating factor is found by finding the exponential to the power of the integral of 2 tan x dx. And that, quite simply, is equal to e to the power of 2 log of sec x. And I'm putting it in curly brackets for now. So that can be rewritten as e to the log sec, well, we just call it sec squared x. It's sec x all squared, which is exactly the same thing. And so e to the power of the logarithm of anything is just whatever that anything is. So that becomes sec squared x. So now we can multiply sec squared x right throughout equation 5. And if we do that, we get, and I'll just make sure I'm not cutting that bit off the top, we get sec squared x dv by dx plus 2 tan x sec x, sec squared x, we'll put brackets around there, and that's times v equals 2 sec cubed x. Now, if we scroll down a little bit, I think we call the previous equation equation 5. So we'll call this equation 6, right? Now, the left-hand side is quite easy to integrate. So what we could do first of all is write it in differential form. So we've got d by dx of sec squared x. You always write that down first. Sec squared x. And of course we've got this v here. So we always take this part and then this part and write them down in this form like so. And that is equal to 2 sec cubed, isn't it? 2 sec cubed x. And we call that equation 7. Right, now then, it's again very easy to integrate the left hand side because that just gives us v sec squared x, and that's equal to the integral of 2, or 2 times the integral, sec cubed x dx. Okay, now I'm not actually going to go through the integral of sec cubed x. Hopefully you can work that out for yourselves and verify the result that I'm about to give you. I worked the integral of sec cubed x out on a mathematical package, and you can do this excuse me, you can do this on mathematical packages like Maple, Mathematica, and MATLAB. You could even do it on Python, which is a free mathematical package as well. So hopefully, if you know a little bit of programming, you would be able to find this integral very easy using those computer packages. Otherwise, you will have to try and persist and work out the integral of sec cubed x by hand. I'm just going to give you the integral, and so the left hand side, v sec squared x, is equal to, and it turns out if you integrate all of this, the 2 sec cubed x, we get the logarithm, the natural log of, in brackets, cos x over 2 plus sine x over 2, close brackets, divided by cos of x over 2 minus sine x over 2, and there's a little bit added on, which is sec x tan x, and I've just squeezed that on, so I'll have to write the next bit in smaller writing. So v will start off right over at the left hand corner, therefore v is equal to log, and I'm going to write it like this, log of cos x over 2 plus sine x over 2 divided by cos of x over 2, make that look a bit more like an x. Just let me rewrite that again. So cos x over 2 minus sine x over 2 plus sec x tan x, all divided by, and let me see if I can get that line straight, all divided by sec squared x. Now we're nearly there. We've nearly got the solution because we know, but we know that v equals 1 over y squared. So if we just substitute in 1 over y squared into the left-hand side for v, we get, just scroll up a little bit, so we get 1 over y squared is equal to the logarithm of cos of x over 2 plus sine of x over 2. We'll close the bracket there, and that's divided by cos x over 2, just as before, sine x over 2 plus sec x tan x. And by the way, there should really be a constant in all of this, but we'll just ignore the constant for now, and that's divided by sec squared x. Okay, so oops. So if we multiply both sides by y squared, or in other words, if we invert both sides of this equation, we get y squared is equal to sec squared x all divided by the logarithm of cos x over 2 plus sine of x over 2 divided by cos x over 2 minus sine x over 2, and then close bracket plus sec x tan x. Okay, so quite simply, the solution, assuming the constant of integration is 0, in which case this solution will be correct, becomes y equals, you take the square root of the top and the bottom, you obtain sec x all divided by, and I'm going to try and get that line straight, a nice big long line, times, let's just scroll up a little bit, there we are, times, right, so we put the brackets in, sec x all divided by the logarithm of, and I'm going to write it out again, cos x over 2 plus sine of x over 2, all divided by cos x over 2 minus sine of x over 2, and then plus sec x tan x all to the power of half. And that is a solution. If you had included the constant of integration that you invariably get with integrals, then there would have been an additional constant over here. So really we should have added the constant on, like so. It doesn't really matter that much in this case. So there should have been a constant added on there, and then in the final solution here there would have been a constant added on to the denominator there, and there would have been a constant added on there. So basically that is how it is done. So until the next video, I hope you found that helpful, and I'll bid you farewell and look forward to seeing you in the next video. So thank you very much for listening, and bye. Bye-bye.